Welcome back. And we're moving on over here. Sorry about the delay. It's going to take a little longer today to get material ready. We're going to look at the smallest rings possible for organic compounds, cyclopropane being the smallest. What I've done is I've drawn cyclopropane here, trying to show the geometry, and my eye is looking at carbon 1 with carbon 3 behind it. So here's what my eye is looking at right here. Carbon 3 right behind it has a hydrogen right behind the hydrogen A on the first carbon. And B is right behind, in front of, sorry, D. B is in front of D. So my eye is looking right here. And here's the other carbon 2 over here with hydrogens F and E. Now, cyclopropane is a very rigid molecule because its ring is so small. I usually try to rotate the bonds in the toy, and I can't because there's no sigma rotation in cyclopropane because of its small size. That means that there's eclipsing here and here. And if we go back to our original, that's this and this. There's also eclipsing between B and D. And if I had my eye looking here, there's eclipsing between F and C and E and D. So that's 6 sets of eclipsed hydrogens. This is not a good situation. It's called a form of strain. Eclipsing, I tried, oops. Oh, it is there, okay. Eclipse, let's start with this. Small rings have limited sigma rotation. That makes H's eclipse each other. Don't worry, I'll move these comments. The inability to rotate, I'm going to throw a word in here, torsion the H's away from each other. Really bad typing. Other causes torsional, spelled that right? Yeah, strain. That's important stuff. Yeah, here we go. Still have that highlighter on, don't I? Sigma rotation can also be called torsion. Now, if you're an engineer and you're in the car industry, there's no desire at all for the frame of the body to be able to undergo torsion, which is twisting like this. That would cause irreparable damage to the car. So there's torsion bars that prevent it. Well, small rings are like they have torsion bars, and this thing cannot rotate. So torsion is just another word for rotation. And by preventing torsion, you cause torsional strain. What prevents it? Small ring size. So torsional strain and eclipsing should be thought of always together. There's another form of strain that comes straight from the fact that we have these angles inside of a triangle, 60-degree angles. We're talking about carbons that are sp3 hybridized. sp3 hybridized carbons want to have a 109.5 degree angle to have zero angle strain. They are prevented from doing so. In a triangle, you have 60-degree angles. You're stuck with them. This is called angle strain. That's one type of strain. One type of strain is called angle strain. And the other kind of strain is called torsional strain. the combined effects of angle and torsional strain give cyclopropane a very unstable existence. Cyclopropane does not like being cyclopropane. As a result, there is very little occurrence of cyclopropane or any organic molecules with ring size 3 in nature. When I say very little, I mean we have maybe 10,000 molecules with that ring size in them out of the trillions of molecules that exist in nature. That's 0%, isn't it? Doesn't mean they don't exist. It means they're very rare. Why? They suffer from a severe angle strain and torsional strain. Cyclobutane does not really improve the situation. When you get to a bigger ring, one thing happens that's favorable. The rings get more flexible and the sigma rotation becomes more possible. But we're still limited with cyclobutane to only a slight amount of rotation. So I'm trying to show it here. It's hard in 3D. My apologies for this gaudy looking eyeball. Oh, by the way, if you didn't know that was an eyeball, that's an eyeball. Okay. And you'll notice that A and C here are a little further apart than here and here, where they're right on top of each other. That rotation maybe was 12 degrees. Remember, 60 would be ideal, and you only got like 1/6 of the way there. So you have partial eclipsing. And the story's a little worse than that. We have 4 H's on top. 1, 2, 3, 4. This is eclipsed with this and this partially. And this is eclipsed with this and this partially. That's 4 sets of eclipsing on top, 4 more on the bottom. Partial eclipsing times 8 total versus total eclipsed times 6. The amount of eclipsing strain is almost identical in total. When you add up all the partially eclipsed in cyclobutane, it ends up being about the same amount of strain as the total eclipsed in cyclopropane. Sorry, I'm distracted by the ice cream truck, which you no doubt hear in the background. We'll get through this. Okay, the angle, normally in a flat figure, right? In a flat geometric figure, hydrogens on adjacent carbons will always be right in front of each other, which is eclipsed. As the rings get larger, there's less rigidity, so sigma rotation can happen to a greater extent. Once again, in cyclobutane, there's still not a lot of sigma rotation going on. 12 degree maybe? I don't know. The carbon angle only changed by about 2 in a negative way. Normal cyclobutane is a square, right? Angles inside of a square, 90. We actually sacrificed and created more angle strain to get this partial eclipsing here. It's a trade-off. So what's worse? 3 angles of 60, that's 3 terrible angles compared to 109.5 versus 4 bad angles of less than 109.5. Once again, it's a trade-off. They're about the same. The eclipsing and angle strains in cyclopropane and cyclobutane are roughly equal. And my neighborhood, the kids got their ice cream and we're free. All right, so in nature, there are only several thousand cyclobutane molecules or molecules containing ring size 4. These are rare ring sizes in nature because of the strain. So remember, there's 2 types of strain. Strain caused by angles being less than ideal. So when we're talking sp3, angles that are not 109.5. And there's torsional strain caused by H's either eclipsing or partially eclipsing. And that brings to a close cyclopropane and cyclobutane. I'm going to go get cyclopentane, which is a much improved story. This looks pretty good. Let's just steal it. Where am I? Cyclopentane. It even says right there in the book, it's different stories. And there's a typo that's been there for since what, 2012. Nobody said anything. Just saw it right now. Maybe it's not in your book. Maybe it's just mine. Millians. Millions.
Dr. Whitaker?
Yes.
I have a quick question.
Sure.
I understand, like, I read this whole section and everything, like, really clicked with me, but one thing that I kind of got confused with was the way that we draw the things from before with the circles and everything. I forget their names because I read this yesterday.
Like how you draw the pentagon?
The Newman models, sorry.
Oh yeah, the Newmans from our previous page 1.
I get really confused with those still.
Okay,
I don't understand, like.
There's going to be a day, you've probably looked ahead a little bit at one of the practice exams, which is really good. And you were asked to draw a Newman with a certain carbon in front and a certain carbon behind. Is that where we're going with your question?
Yeah, and the homework problems as well. I just took a look at those.
Yeah, I hear you. I'm going to devote a segment of review to that very topic because it is a skill that you need some pointers on. I wish I had those pointers when I was being taught my first time because I struggled with it exactly like you're doing right now. Right now, I just want the general ideas of the conformations and things being in front of each other. And then I'm going to give you some good tips about how to actually draw Newmans when you're forced to look at a molecule a certain way. So that's going to come up. You got to wait for me, okay? Some questions are so good they're ahead of us. All right.
Appreciate it.
You're welcome. And yeah, cyclopentane and cyclohexane are entirely different stories. Once again, you don't want a flat figure for any of these geometries because you'll have eclipsing that's terrible. When you get to a pentagon, I don't want you to memorize in a normal pentagon, the angle is 108, which is kind of a nice number compared to 109.5. But that's if it's flat. By pulling up one of the corners. So if you kind of just use your imagination here, grab this corner and kind of sigma rotate it up to here. Maybe you can see how this becomes this. I kind of kept these corners the same, 1, 2, 3, 4, 1, 2, 3, 4, and then I kind of just sigma rotated up to here. And that really helped out G compared to this H here. It put it in between this H and this H. You can't really see it here. Here's where the toys would have really helped. All I'm going to say is that corner you rotated made these 3 carbons, just trust me on this, if I had the toys it would prove it, those 3 carbons are perfectly staggered. We haven't seen staggered in a while, right? That's with the H's evenly spaced from the front carbon to the back and coming back to the front carbon again. So we've eliminated eclipsing on 3 out of the 5 carbons by just pulling this corner up and rotating the sigma bonds. We still have the same issue with A and C being right in front of each other and B and D also. But that is only 2 sets of eclipsing, just 2. And you can do the same rotation that you did with this corner instead with this corner. In fact, that's what it's doing all the time. Cyclopentane is rotating each of its corners to be like the top of an envelope where there's a triangle. I know you guys don't mail stuff anymore, but you know an envelope still. I hope we haven't totally lost that point of reference. And the part you lick is triangular shaped, and that's the corner I pulled up. So you can imagine me closing my envelope here and sealing it, right? Well, each of the corners can be made into that triangle just by rotating around. So even though you do have eclipsing times 1 times 2, you're moving it around the molecule. So it's kind of a similar phenomenon to resonance stabilizing electrons by moving them around in a molecule, except it's for removing torsional strain, isn't it? When we can get rid of some eclipsing, we're getting rid of torsional strain. Angle strain is never a bad situation with cyclopentane. Even with a 108, it's well, very close to 109.5. And even when we did this triangle up here and shrunk it down to 105, this is not a strained angle. You actually learned more about angles than I taught last week when we learned our 3 angles, right? You always said water, oh, those lone pairs, they repel more than the bonding pairs. The angle goes closer to 104. And you didn't have a problem then with an sp3 oxygen having a less angle than 109.5. And you probably didn't even talk about the oxygen being sp3 at the time, but now you know. So if you're within 5 degrees of an ideal angle, that angle strain is virtually 0. And 105 is within 4.5 degrees of 109.5. So you've got almost no angle strain to start with in cyclopentane. You've got eclipsing, which causes torsional strain, but it's only on adjacent carbons that keep rotating around the molecule as you move the triangle around. So the total strain is very little. There are trillions of molecules in nature with this ring size. Just think about DNA molecules. Aren't there ring sizes 5 in there all over the place? Yeah. And those things aren't falling apart. They're very stable. Ring size 5. Envelope is the conformation to remove some of the torsional strain. And it's got almost 0 total strain. And this should be millions and really trillions if you think about it. In the book, it refers to known molecules, but we know there's more than known molecules out there. Now, I know it's going to be a short segment, but we're going to devote about 40 minutes to cyclohexane. So I think it's a good spot to stop here and pick it up and do a longer segment in our next one, okay? So we're going to pause or stop, sorry. And I will see you very soon.